Jonathan Doolin here. I am working on my triple conjunction conjecture, and I wanted to find out how far do Jupiter and Saturn go in retrograde. So I think I need a certain amount of data, and for Jupiter and Saturn, first their distance from the Sun, and I've looked those up on Wikipedia and found those to be 5.2 astronomical units and 9.5 astronomical units. Uh, Next, I want the amount of time that they are retrograde, and the reason I'm choosing this is because I couldn't find anything that told me how the angle subtended during their retrograde time. So, but I did find this, and I'm hoping I can calculate it from this. So I found a site that told, or on Wikipedia under a retrograde motion page that Jupiter goes 121 days in retrograde and Saturn goes 138 days. And finally, I'm going to need the length of their years, how long it takes for these planets to go around the Sun. A NASA website tells me that Jupiter has a 4,333-day year and Saturn has a 10,759-day year. Now, with that data in mind, let's consider the Sun and whichever outer planet. This is the Sun, then the planet Earth going around the Sun, and then the outer planet that's coming around perhaps up here. And then we want to consider the where Earth is and where that planet is when when the retrograde motion begins, and then Earth will come around to there, and that planet will come around to, say, there, and where that ends. So basically, I want two triangles, and I don't want it to look like that. I want it to look like this, so that we have kind of a little bitey claw thing. That's the way we're going to kind of picture it. So Earth begins to see the retrograde motion here, and notice this angle is moving backwards. So this is our vector, our line of sight vector, and then towards the end, this will be our line of sight vector. And after that, the planet would go back into prograde motion. So then let's talk about what we know. We know this distance, because that's the distance of Earth from the Sun. It's 1 astronomical unit. We know this distance. This is the distance of that the far planet from the Sun. It is either 5.2 or 9.5 astronomical units. We can calculate this angle because it's going to be oh shoot, 3, 2, 1. Hi. So here is a picture of what we have in mind. The far planet is going along this arc. Let's say we're dealing with Jupiter for the moment. The distance from the Sun to the planet is 5.2 astronomical units. Now it goes around the Sun every 4,333 days. So we could calculate this angle here based on the fact that it's 121 out of those 4,333 days. this is the distance around of the Earth going around the Sun. And we could calculate this angle here based on the fact that it's 121 out of 365 days. So that angle can be found. We know the distance here because it is the distance from the Sun to Jupiter, and this is the distance from Earth to the Sun, which is 1 astronomical unit. So we got several things to fill out on this triangle. I think I will redraw it like... Actually, let's first, before we redraw it, let's give these variable names. I'll call this one R, big R. Time retrograde, I'll call small t. The year, I'll call big T. So then, with those numbers in mind, I'm going to draw one of these triangles. Okay, let's see. And in a larger fashion. And we'll call this R. That's our distance from Sun to the big outer planet. We'll call this 1, of course. We'll have an angle here, which is based on the angle subtended by the large planet, which will be T over T would be the little t over big T would be the portion of the circle. Well, actually, I cut that angle in two, so it'd be half. So I will, instead of multiplying this by 360, I will multiply by 180 to represent half of that full angle, which would be 360 times t over t. And then we'll have another angle going from here to here, which is how far Earth is going between there and during that time, which is t over 365, an Earth year. I guess you could make it t over 365.25. And I'm going to multiply that by, also by 180, because it's half of the time. So we can find this angle by subtracting the two, which would look like, I'll just write it out while it's paused. Okay, the two terms share a common factor of 180t. So we can write 180t times 1 over 365 minus 1 over t. So that is the angle. Now at the end of the day, though, the angle that I really am interested in finding, or the two angles that I'm interested in finding, is like if I take this one vertical and this one vertical, finding this angle plus this angle. There's a symmetry there. But on here, we've got this vertical line, and then we would put this vertical line in there. And we want this angle here to be found. Now with this side angle side, we have sufficient information to find out this side, this angle, and this angle. So we can calculate everything in that triangle. Okay, here's my idea. We've got this triangle that goes kind of like this. We know we know alpha, beta, gamma. We know all the angles inside there. We know those two lines are parallel. We know this angle is delta. And so if those lines are parallel and this line comes through there, then this angle here is delta plus alpha, and this angle here would be 180 minus alpha plus gamma plus delta, alpha plus gamma plus delta. So that would give us the final answer. Okay, looking at Jupiter, I calculated the 180 times t over capital T to be 5 degrees, about, or 5.02 degrees to 3 significant digits. Alpha, which was this angle here, is just 180t times 1 over 365 minus 1 over t, came out to 54.6 degrees. Now I'm trying to find a gamma, but before I get gamma, I don't know a rule to get it directly, so I'm using the law of cosines. L equals 1 squared plus 5.2 squared minus 5.2 times 1 times the cosine of 54.6, and take the square root of that. Comes out to be exactly 5.00 astronomical units. I'm going to actually put that in the table up here for both of those. So let's call this angle alpha and this angle, this distance r. We can use the cosine law to say, the sine law to say sine alpha over L equals sine gamma over r. So gamma is going to be equal to the sine inverse sine of r over L sine alpha. Okay, it looks like I've miscopied the law of cosines. There is a factor of 2 here. I'm actually at a point where I've kind of finished, but it's coming out like a answer that I do not think is conceptually reasonable. Because for this to be half of the distance that Jupiter goes retrograde, that would mean the whole distance was over 120 degrees, and I just don't see that being a viable possibility. Okay, I've been working with a spreadsheet for a little while here, and I think I found the mistake right here, where I have 64.4 for gamma. What I am neglecting is that 64.5 is not the angle here. We can look at this picture and see that this is not an acute angle. It is a obtuse angle. So what we need to do is we need to take 180 minus 64.4 to get this value, which when I'm done, Jupiter looks like it is at 4.78 degrees for the half angle, or 9.56 degrees for the full angle. So the full angle subtended by Jupiter in retrograde is about 9.9, just about 10 degrees of right ascension, which is not the 30 degrees that I had hoped to get it all the way from Capricorn to Pisces, but it's about enough to get it to either come from Aquarius or from, I think it's called Aries. And now that I've done that in the spreadsheet, I could copy it over and see how far Saturn travels in retrograde, and it seems to be about 6.84 degrees. So here is all of my work again as an algorithm to find the angle subtended by an outer planet, let r equal the solar distance to that planet in astronomical units. Let t be its orbital period, while little t is its time in retrograde. Then we find epsilon is the angle subtended by Earth during the retrograde period. That's pi t over 365.25. I'm using radians here instead of degrees. Delta represents the angle subtended by the distant planet, pi t over big T, its period. A triangle is constructed with the Sun at one vertex, the Earth at another vertex, and the distant planet at the third vertex. This is the condition at the retrograde start. You could also use the retrograde end. The distance from the Sun to the distant planet is r. That's one part of the triangle. The distance from the Earth to the planet is L, and the distance from the Sun to Earth is 1 astronomical unit. So L then is calculated via the law of cosines. L equals square root of 1 squared plus r squared minus 2 times the cosine of alpha. Then gamma is calculated via the law of sines, taking into account that it is an obtuse angle, so gamma equals pi minus inverse sine of r over L sine alpha. And then finally we calculate how far the line of sight vector from Earth to the distant planet is changed, and we call this final answer theta. So theta is equal to 2 times 180 degrees minus alpha plus gamma plus delta. When values for Jupiter are used, a path of 10 degrees of retrograde right ascension is found, while Saturn yields 6.8 degrees.